Good afternoon, morning, or evening, whatever suits you where you are. Welcome to another Taco Tuesday. My name is Brett Zerba, and many of you have been through these before, so you kind of know the routine. But I will again introduce myself as an application engineer, training engineer for Taco. I've been with the company almost 25 years, and I will moderate today's event. Before we get started, can you do some hand waving? How about my friend Warren? Can you wave your hand out there to make sure you can hear me and see the screen? Okay, good. I see some people waving their hands. Thank you very much. I appreciate that. So that's a good start. That's always a good start that you can hear and see us. Technology, I mean, we haven't had many, I shouldn't even say this, glitches recently. You know, I just jinxed this, right, Rich?
Yeah,
Rich
no,
Medeiros, I know that was a bad thing to say. As soon as I started saying it, I knew I made a mistake. So today's presentation is on expansion tanks. You know, the types, the sizing, selection. Word on the street from some good friends of mine to tell me that we have a very easy app to use to select expansion tanks. So hopefully you can agree with that as you go. And as most of you know, please ask questions. I'll be moderating the questions, and that's how these seminars, that's how they really hit home and really do a good job, is if we get interaction from you and we can answer your questions. And to be truthful, if you have a situation about an expansion, type it in there. Maybe all of us can learn. And trust me, I learn on a daily basis. So as most of you know, 24 hours after today's webinar, roughly 24 hours, you'll get an email with a link to the recording and to a PDH certificate if you so require one. So be on the alert for those, and I haven't seen many emails about people not getting that, so that system must be working pretty good. There are no handouts today, so don't even look down there. Well, and if you've already done that, well, no, you don't have to. So as most of you know, Taco is a privately held company, third generation. Johnny White is the current family owner. His grandfather started it, as you can tell, over 100 years ago, Elwood White. Some of you may have seen some of the slides that were popping through a little earlier. And he actually purchased the thermal appliance company in 1920 down in New Jersey, and then he moved to Rhode Island in the 50s, maybe even a little earlier, first to Providence and now to our headquarters in Cranston, Rhode Island. Where we've been located for many years. But we are a worldwide company. We have a facility nearby to Cranston in Fall River, Mass. Some of you, geography, that doesn't make sense to many of you, but it's only 20 minutes, 30 minutes from Cranston to our facility in Fall River, Mass. And that's where these products are actually fabricated at our welded products division located in Fall River, and that opened up in '83, I believe, '83 or beginning of '84. So it's been there for quite a while now. And there's roughly 80 individuals there, and they do run 2 shifts. And I believe I heard yesterday that they're on mandatory overtime because of some of the scheduling requirements, all the orders you folks are putting in. So that's all good news. So anyways, and then we have a facility in Canada, Milton, Canada, and we've been in Canada since 10 years after we started, since the early 30s. We've had a presence in Canada, and then we have a facility in Czechoslovakia. We have a facility in Italy. That's where our high-end circulators are made for the European market, and we purchased that facility not too long ago. And then we actually have a foundry in Vietnam, that does some of our stainless steel work, amongst other things. And I actually think they do some beer tap work for a company as well. I haven't seen that product. Maybe they can get me a sample. I wouldn't mind that at all. And then, as hopefully some of you know, we purchased HydroFlow pumps a few years ago, and they're headquartered in Nashville, but they have 3 facilities in the United States, one in Texas, one in Arkansas, and one in California. And they do vertical turbines. So we do have that, and any of your TACO reps or our website or whatnot can get you a lot more information on our vertical turbines, not just for HVAC, but for municipality, wastewater treatment, and other products as well. And then we also just released in the States and up in Canada a booster line. So we do have pressure boosters for the maybe more for domestic, you know, to keep the proper pressure at the top of that high rise that you're working on. So, and again, you can get a lot more information on that as well. But that's a quick introduction. And if you please ask the questions, please ask questions. Like I said, Rich Medairos will be doing today's. He'll be the main presenter today. He has presented this in the past, maybe about a year ago, and it's always goes over well. And expansion tanks are one of those products that it's an important part of an HVAC hydronic system for many different reasons. And I don't know, Rich might even get into the Boyles Law, for God's sakes, this afternoon. We shall see. And as you can tell, he's quite the artist. And he has a smiley face on, and he'll tell you why, because he's nice and comfortable at his house. And he wasn't yesterday or over the weekend, and maybe he'll let you know about that. So I think I've yapped enough, Rich. Why don't you take it away, my friend?
You know, thanks, Brett. I appreciate that introduction. Just a quick intro for myself. My name is Rich Medairos. I'm a mechanical engineer and a senior systems engineer here at TACO. I spent the majority of my career on the consulting side of the industry, and I specialize in the engineering and design of HVAC systems. I am registered as a professional engineer in a couple of different states, and I've been at this for several years. And I've been with TACO, I'm going into my 10th year. Can you believe that? Not quite 10 years yet, but I'm going into my 10th year. Seems like I just started yesterday, Brett.
I know, it's pretty crazy.
Crazy stuff. So we're going to talk about expansion tanks today. And if my computer is working the way it's supposed to, why do we need expansion tanks? It's the very first thing we're going to talk about. Types of expansion tanks. We're going to touch on Boyles Law. Boyles Law is the physics that helps describe how an expansion tank works. Expansion tank sizing, we'll introduce you to the TACO expansion tank sizing app. It's very good. And we'll do a couple of selections for expansion tanks. We'll also talk about the impact the location has on the size of an expansion tank. And then questions. And as Brett said, if you have questions, please type them in. You don't have to wait till the end of the discussion. Brett will ask me to pause periodically so that we can answer your questions in real time. So here we have a very, very simple diagram. This diagram is intended for class discussion only. It's not intended to be a system that you should copy and paste and use it as a system design. So why do we need expansion tanks? Well, in a closed loop pressurized system, which is what we're demonstrating here today, an expansion tank allows the fluid to expand as a function of increase in temperature. Now, if for some reason we did not have an expansion tank, let's just put a big X through this expansion tank here. If there was no expansion tank and this happy little boiler over here was doing its thing and heating up the water from initial fill temperature, which usually is around somewhere around 50 degrees, could be a little bit lower or higher, degrees Fahrenheit, that water will expand. And if it has no place to expand to, it will break something. Now, hopefully someone has been diligent enough to include safety relief valves like we've shown here on this boiler in strategic locations so that if the fluid does expand and for some reason the expansion tank is waterlogged or it's isolated from the system or it has not been installed yet, the safety relief valve will go off to protect the system. But if there's no safety relief valve and the water does heat up, it will expand. And if it has no place to go, it will break something. And usually it'll break something like the terminal equipment. We've shown some arbitrary fan coils in this diagram, or it could break the boiler, or it could break the pump or the piping, but it will eventually break something if the water has no place to expand to and the safety relief valve did not go off. The second reason, which is also extremely important, is that the expansion tank needs to be connected. In this case, it's connected to the suction side of the pump. Here's the suction side of the pump over here. And this is known as the point of no pressure change. So the expansion tank is responsible for controlling, is partially responsible, let's use that term, for controlling the pressure in the system. So it performs two very important roles. One is to ensure that there's a place for the water to expand to, and the other is to control the pressure in the system. Okay, so we're going to get into expansion tank types in a moment, but any questions, Brett, that popped up?
Just a comment. Well, someone made a comment. They didn't really realize that its second function, it had a second function, but that is a very important function, as you just said, to control the pressure in the system.
Yeah, extremely
Someone
important.
commented
And so
on
we
that.
will touch base on that in detail.
Yep.
All right. So we're going to talk about the types of expansion tanks. And initially, by the way, I'm going to show you just a list, but don't worry about the list because I'm going to get into some photographs so you can get a real good idea of what these things are all about. So let's just list them first. So we have plain steel tanks. The second category is bladder style tanks, and that can be subdivided into two styles. One is called a full acceptance bladder style tank, and the second is called a partial acceptance bladder style tank. And again, I will define these more carefully in more detail in a moment. And then the last category is called a diaphragm style tank, and that is a partial acceptance tank. So there you have it. It's as simple as that. They're either plain steel, bladder style, or diaphragm style. Those are the most common, and those represent the types of expansion tanks that we manufacture and offer to the industry. Okay, so the very first one on my list is a plain steel tank. Just as the name implies, it's nothing more than a steel container. And typically it has 4 connections. On the left side here, it has connections for a sight glass. So I'm just going to make an imaginary sight glass here. And that sight glass indicates the water level that's in the tank. So if the water level in the sight glass is here, then the water level in the tank is the same. And then it has 2 connections at the bottom. Generally speaking, one of those connections goes to some type of blowdown valve. It's a manual valve, and that's to allow the operator to empty out the tank. And usually that goes to a floor drain in the mechanical room. And so if the water level gets too high in the tank, they can use this manual valve and reduce the fluid level in the tank. And usually it goes to pipe to the floor drain. It doesn't have to be piped to a floor drain, but generally it is. That's what we normally see. Okay, and then the other connection goes to the system. And all I'm going to do is have a broken line here and just call it the system. I'm not going to show any details for the piping on the system. When it comes to the expansion tank, that's pretty much all there is to a plain steel tank. So just to make sure that everybody's on the same page, the lower half of this tank is filled with water and the upper half of this tank is filled with air. Now, one of the sort of drawbacks to a plain steel tank is that the air is in contact with the water, and over time, the air actually goes into solution. So the air gets absorbed by the water and the water level rises inside the tank, which is why you need a sight glass so you can see where the water level is, and then you can adjust the water level by opening this manual valve and allow some of the water to come out of the tank. So any questions about a plain steel tank?
Someone just typed in, what are some typical sizes of these tanks?
Oh, we can get them in a variety of different sizes. You can get them from a few gallons up to several hundred gallons. And we can actually build a plain steel tank for custom design And if you come to our facility in Cranston, Rhode Island, we have a couple of plain steel tanks in our test lab. And those plain steel tanks, I believe, are 10,000 gallons each. So we have a total capacity of 20,000 gallons. So yeah, you can get them in just about any size you want. I believe if we have some time at the end, I'll go in real time to our website and show you the sizes that we catalog, but you can contact your manufacturer's rep and they can always design and build a custom tank for your needs.
Here's a great comment / question. General Chad says, I typically see these in older systems. Are they used in new systems at all?
The overwhelming majority of new systems today use bladder style tanks, and we do occasionally see a plain steel tank in a new system, although they're very rare. The main reason that people probably don't use them anymore is because of, as I said a moment ago, the air comes in contact with the water. Eventually the air will be consumed or go into solution into the water, and so the tank becomes ineffective. So it's not the most reliable tank. It requires a substantial amount of weekly or monthly maintenance, as opposed to, and we'll talk about this in some detail, bladder style tanks. The water is not in contact with the air, and so it's much easier to have the tank operate pretty much trouble-free for a significant period of time.
Christine's got a nice, a pretty good question here. As all questions are, is there a pressure relief as the water level rises?
Well, whatever relief valves or systems, those are external to our tanks. So if the design engineer prefers to have some type of relief valve in the system, they would put it as part of the piping. It's not part of the tank itself.
Excellent.
Okay.
Then someone asks, well, yeah, what is typically the air? Half and half? What portion?
Well, it depends on the pressures. And so one of the challenges we'll show you in a few minutes when you select a plain steel tank is that if you have a minimum pressure, maximum pressure, it determines the relationship between the fluid and the air. And when we talk about Boyles Law, you get a better understanding of that in a few minutes. Okay.
Yeah, why don't you go on? We got a couple questions, but I think I can work them in at different points in the presentation. So sit tight,
Okay.
folks, if you've typed in a question.
These are great questions, Brett.
Yep.
All right, so let's go and look at the next category, and this is called a bladder style tank, and it's called a full acceptance. And in the TACO world, this is called a CA, Charlie Apple tank. So I'm going to get my pen over here, and we're going to look at the cutaway. That's the little green guy over here, and you can see the steel container. That's the first thing I'm pointing to. And then we can see the bladder. This is a rubber bladder, so I'm going to point to that. And then we see the air space. There's void space between the bladder and the steel tank. Again, this is a cutaway. So there's the air. Inside the bladder, eventually, that's where the water will go. So I'll put a W for there right now. So a full acceptance bladder style tank has a bladder, it has a void space where the compressed air goes, and it has the steel container. And it gets its name full acceptance because the bladder can hold the same physical volume as the steel container. So in our simple example, if we, for example, say the steel container is 200 gallons, then that means that the bladder will also hold 200 gallons. So one of the nice features about this style tank is that if for some reason, let's say someone inadvertently left the Schrader valve. The Schrader valve, by the way, this is a Schrader valve on the left side over here. It's the same type of valve that you find on your car tire. It was invented by a gentleman by the name of August Schrader around 1891. And this is quite a little device because We use them in our expansion tanks, and they're it's kind of hidden in this photograph. They're behind this collar right here. So inside there is where the Schrader valve is, and that's where you add the compressed air. And when you add compressed air, that'll be where I put this letter A, the void space over here. So the Schrader valve is used for our expansion tanks. Most expansion tanks use the Schrader valves. You find Schrader valves in your car tires and your bicycle tires. I mean, there are literally millions of them out there. So it's a very simple, very reliable device, and it allows us to add compressed air to the void space between the bladder and the steel container. And again, this is a full acceptance tank, which means that the bladder can hold the same volume of liquid as the steel container. So in our case, if the steel container is 200 gallons, that means the bladder is also 200 gallons. So if for some reason someone should inadvertently bleed the air out and water fills the bladder can expand to the full steel volume of the tank because it's a full acceptance bladder. So we've talked about this particular type bladder style tank. It's full acceptance. It has a Schrader valve for adding air to the void space, the compressed air. It also is serviceable. You can take this part at the top here, this big flange off, all these bolts in this flange, and you can physically remove the bladder. So if for some reason the bladder should fail, and bladder failure is very rare, if the bladder should fail, you can remove the top and you can take the bladder out and put a new bladder in, bolt it back up, and you're back in business. Fairly short period of time.
Rich, as you're talking about replacing a bladder, we need to get your opinion. John's asking the question, some manufacturers have the connection on the top, some on the bottom. Which arrangement more facilitates replacement of the bladder? I know what you're going to answer, but why don't you do some words?
Well, you know, that's a great question, and I don't think Ron is on the call with us today.
No,
Ron
he's
Feller.
not.
He would have a much better answer. I prefer it to have the connection at the top because I like the idea of taking the bladder out of the tank at the top, similar to the CA model. But
I mean, if you think
we do
about
have,
it, if it's on the
we do have
bottom and it's floor
bladders that are
mounted,
serviceable from the bottom. So
yeah. If it's floor mounted though, it's going to
yeah,
be difficult to take it
it's
from
difficult.
the bottom.
But yeah, I prefer this. If Ron is with our fabricated products group, and he could give you a couple of different opinions about that. So this is kind of an opinion more than anything else, but I prefer them at the top. I think Warren is on the line. Isn't Warren out there in Never Land?
Yes, he is.
Warren to type in what he prefers, and then we'll tell the audience. Warren is one of our manufacturers reps, and he sells a lot of expansion tanks to customers. So, any other questions, Brett?
Yes, we got a couple about these. What would be the best expansion tank for an ethylene glycol system?
Well,
That's
ethylene glycol. I mean, the two most common glycols are ethylene and propylene. And for our product line, our bladders are compatible with both fluids, both ethylene and propylene glycol. So as far as the ethylene and propylene glycols are typically used in HVAC systems for freeze protection. So they are compatible with those two fluids.
And someone's asking, can you repeat why you need the Schrader valve for adding air? Is this just for initial pressure?
Yeah, we're going to get into that in much more detail in a few seconds. So if we could just hold off on answering that and be sure to ask that question again, Brett.
Okay. And then the horizontal, vertical, is there any recommendation for selection? The stained stainless steel was horizontal. This one's vertical.
Yeah, so some of our bladder style tanks can be mounted horizontally. I would have to actually take a few minutes and go through our installation manual to tell you which ones are which. So some of our audience probably knows off the top of their head, but I'd have to look it up. But yes, some of our bladder style tanks can be mounted horizontally. I just don't know which ones, but that's a great question. I should probably have a list of those for future reference.
To be quite honest, most of the ones I see are vertical, but obviously in some mechanical rooms you might want to tuck one horizontal.
Yeah.
But there are some options out there for you to do that.
Okay.
Onward and upward, my friend.
So now let's go to the next style tank, which is called a partial acceptance. And again, as the name implies, we're going to use the same kind of thing. So our cutaway is on the right side. And let's assume that, again, that our steel container is 200 gallons. And as you can see in this case, the bladder is physically smaller. So there's the void space. That's where the air goes. In this particular case, the bladder is mounted at the bottom, and so the connections, you can't see it, but there is a pipe connection at the bottom here for the water side. So the bladder contains the water. So inside the bladder is the water, the void space is the air, and there's the steel container. And if we said, for example, that the steel container was 200 gallons, I'm going to make up a number, and let's say the bladder is smaller than that. The bladder, I'm just going to make up a number here and say the bladder is 50 gallons. Well, because the bladder is less volume than the steel container, in this case, I've kind of made up a little number here. Then we say that this style of tank is called a partial acceptance. In other words, the bladder can only house a partial volume of the steel container. So that's where that term comes from, partial acceptance. So in our simple example here, if the steel container was 200 gallons and the bladder was less than 200 gallons, then it would be considered a partial acceptance tank. So that's what we've shown here. And again, for the air side, you can see this little collar at the top to protect the Schrader valve, and that's where you add the compressed air over here. And we're going to talk about that compressed air in a minute. And then the last type of tank that we offer, that most manufacturers offer, is called a diaphragm style tank. And again, this is a partial acceptance tank. And again, the reason that we call it partial acceptance is because if, again, the steel container happened to be 200 gallons, the diaphragm can only hold something less than 200 gallons. I'm going to make up another number, not to be confused with any other numbers that I'm writing up here, but let's assume that the bladder can only hold 30 gallons. I'm making these numbers up here a little bit. You'd have to look on our catalog data to find out what the acceptance volume is. But if, again, the diaphragm could only hold 30 gallons, since that's less than the steel container, that's called a partial acceptance. And because it's a diaphragm, it no longer resembles a balloon. It's more like a rubber bowl. So you can see it's connected to the inside of the tank along the circumference of the inside, along the sort of equatorial plane. And then it's kind of like the shape of a rubber bowl. There's kind of the bowl shape right there. Air is at the top and water enters. Now you can see the actual water connection here on this one on the left. So the water enters at the bottom. You can barely see it. The water connection is right over here. You can barely see it, but it's right there. And so this would be the water here. Now, one of the characteristics of a diaphragm style tank is that it's a non-serviceable tank, which means that if for some reason the bladder should fail, the diaphragm should fail, then the expansion tank has to be disposed of. You cannot replace the diaphragm, so it's a throwaway device. Now, someone would say, well, why would you buy a throwaway device? Well, they're relatively inexpensive, and for smaller systems, they are set up properly. They're very reliable. They last a long time. And so chances are you probably would not have to replace the tank if the diaphragm, you would not have to replace the tank within a reasonable period of time. Most equipment of this design, if well maintained, should last at least 10 to 15 years in that order of magnitude. So to replace the tank after, say, 15 years for a well-maintained system is not a big expense. So there's the three categories. of bladder style tanks. We have bladder style full acceptance, bladder style partial acceptance, and diaphragm style. And the ones without the bladder are plain steel tanks. So that gives you a quick snapshot of what the tanks are all about. So Brett, any questions?
Yep, we have a couple good questions. Somebody asked, and you covered it, but I just want to emphasize which tanks are the bladders replaceable. The full acceptance, the partial acceptance, yes. Diaphragm, no. It's not really a bladder. It's, as you can see from this cutaway, but this tank is a throwaway tank.
That's correct.
That's what we call that. And I just want to, Rich has been writing some numbers down, 200, 50, 30, and different numbers there. For all intents and purposes, they are made up numbers. They aren't necessarily what a catalog tells you or anything like that. Isn't that true, Rich? Someone's
questioning.
I'm
just writing so that people get the relative, I'm trying to show that if the steel container holds 200 gallons and the bladder holds 200, they're equal, that's called full acceptance. If the steel container is 200 gallons, the bladder is 50 gallons, then that's partial acceptance. That's the only reason for throwing some numbers out there.
Right. And do you have any symptoms of a failed diaphragm?
Yeah, so if, again, based on what we had just talked about, this is supposed to be the air here, and then the water is down at the bottom. Let's assume that there's a hole here on the diaphragm. Over time, the air will go into solution into the water. The water will find its way through this hole and fill up the entire tank. And eventually, hopefully someone realizes it and does not set off the relief valve. But if it fills up with water, we sometimes say it's waterlogged. So you can actually just take and depress the Schrader valve. And if water comes out of the Schrader valve, then you know that the diaphragm has failed. And that's a very simple test.
And this question always comes up, Rich. Why is there a full acceptance bladder and a partial acceptance bladder?
Well, bladders are an expensive part of an expansion tank, and so the partial acceptance bladders are less expensive. They are not idiot-proof. When I use the term idiot-proof in this context, what I'm really saying is that a full acceptance bladder will hold the same volume as the steel container. In our previous example, if you had a partial acceptance bladder, and let's say it only held 50 gallons, but the steel container held 200 gallons, and someone bled the air out, and now the bladder was filling up with water, if it got greater than 50 gallons, it has the potential of rupturing or damaging the bladder, or failing, the bladder would fail. And so from that point of view, it's more problematic, but it's much less expensive. So cost becomes a major concern in all mechanical systems. So the most expensive is full acceptance, the middle cost is partial acceptance, and the least costly are the partial acceptance diaphragm style tanks. Actually, the plain steel tanks are the least expensive, but they have their own set of issues, which we'll talk about if we have some time at the end. Anything else, Brett?
Yeah, here's a great question from Gordon. Which ones are ASME?
ASME, Association, ASME. Yeah, what does that stand for again? I'm sorry, American Society of Mechanical Engineers. That means that all of our expansion tanks, excuse me, I'm losing my voice. All of our expansion tanks are ASME certified. So our factory is ASME certified. Every product, all of our pressure vessels that exit our factory are ASME, American Society of Mechanical Engineers certified, which means they're built to a much higher standard than non-ASME tanks.
All right, so where'd that question go? Go ahead. I've got to find a question that I need to bring up.
Okay, let's talk a little bit about Boyles Law, because it's the fundamental principle of the physics that control expansion tanks. So Boyles Law was published by Robert Boyle in 1662 in England, and it states that the pressure of an ideal gas is indirectly proportional to its volume at constant temperature in a fixed container. That's extremely important, and we'll see what we mean by that. And the formula that Boyle published back in 1662 was, he said that the pressure, the absolute pressure, I put P pounds per square inch absolute, the absolute pressure times the volume in one condition for a fixed container is equal for the pressure and the volume in that same container. Now we're talking about the air volume, and because this pertains to air, which is a compressible fluid. So by demonstration, let's just look at a couple of containers. And initially, we're going to oversimplify this. These are two containers, and let's just make up a number. And today I happen to like the number 200, Brett. Let's assume
Yes.
that each one of these containers is exactly 200 gallons. 200 gallons. Hey. Okay. So they're both 200 gallons. I'm not going to rewrite it on the right side because I have a method to my madness here. And let's assume that the initial pressure and they're both empty. They're just filled with air and they're both empty. And let's say the initial pressure in this first container is 50 pounds per square inch, PSI. I forgot the zero there. 50 PSI G, pounds per square inch gauge. In other words, if I put a pressure gauge, now let's just, an imaginary pressure gauge up here at the top of this tank, and it would read 50 pounds per square inch, 50 pounds per square inch gauge pressure. Okay, now, and both of these containers, by the way, let's say are connected to a piping system. Now the tank on the right, let's assume that I allow, I'm going to put a valve over here just for the fun of it. You would not, well, I better not do that, Brett, because if I do that, then then I'm going to get myself into trouble. So I'm going to X out this, just pretend that's not there. So we have it connected to a piping system. So if the fluid is allowed to expand and fill up this container, now there's no place for the air to go. I'm not allowing the air to leave the container. It's completely captured inside here. And if I fill that up with water from my HVAC system, so I'm going to ask the audience out there, if I add water, and I happen to add 100 gallons of water, okay? Can anybody tell me how many gallons of air? Because this one on the left, the entire container was air, and now this one has water at the bottom, and I have compressed. And what is the volume of the air up here? I'm going to put the letter A. What is the air volume equal to? Which in this case, that's air, and this would be V2.
We have a bunch of folks typing in Mark and Gordon and Warren 100.
That's right. I would have 100 gallons of air.
Amongst others.
So what's the ratio of my volumes? Well, Boyle's law says that if I had an initial pressure of 50 psig and initial volume of 200 gallons, that's going to be equal in a closed container to my final pressure and my final volume. So if I'm trying to figure out what my pressure is over here, then I want to find out what P2 is. So all I have to do is rearrange this equation and say that P2, look at this, Brett.
You're on a roll.
Really cool here. I'm on a roll here. How are we doing for time, by the way? Oh, not too bad. So P2 is going to equal the initial pressure, in this case P1, times the change in volume, which is going to be V1 divided by V2. So I made the arithmetic very, very simple. So if V1 was 200 gallons and V2 is 100 gallons, then V1 over V2 is going to equal to 2. So the final pressure is going, and this is absolute pressure. Remember we said this is absolute pressure, is going to be equal to the initial pressure, which we said was 50, but that's gauge pressure. So we have to add to that the atmospheric pressure plus 14.7, and assuming that we're at sea level, 14.7 times the ratio, which we said this ratio was now equal to 2. So put that in brackets, times 2. So what is my final absolute pressure? Anybody out there wanted to type that value in, Brett?
We'll see.
Anybody have a number that they can share with us?
Oh, we've got a 114.7 and a 129.4
If I take 50 plus
PSIG.
14.7, right? And I add those two together and I multiply by 2, what did somebody come up with?
129.4
Correct.
PSI.
PSIA,
A.
pounds per square inch absolute. So the pressure is going to be, the final pressure is going to be equal to 129.4, 129.4. Let's see if I can squeeze that in there without losing too much time. And that's PSIA. IA.
And John's comment was, or answer was 114.7 PSIG.
So if you take that 129.7 minus 14.7 to convert it back into PSIG, that final pressure should be equal to, what was the number, Brett?
114.7, I believe, is what he
That's
said.
correct. 114.7
Yep.
PSIG. PSIG. So it's very important that you, if you're going to use this equation to figure out what the final pressure is, always remember to convert it into pounds per square inch absolute. And then if you want to read the pressure on a gauge, to be sure to convert it back to pounds per square inch gauge. So hopefully this little diagram puts to rest the concept of when you have a container that's at initial pressure and you allow the fluid to expand, you're compressing the air, so it's a compressible gas. And in this particular case, I've rigged the ratio so it'd be very simple arithmetic, and you could see the relationship between the initial pressure and the final pressure. Any questions before I go into how to actually size these guys? Because we're kind of getting.
No, why don't you keep going? I have a couple, and I feel bad, but anyways, go ahead.
Okay. So let's keep moving right along here. So expansion tank sizing. So this one I'm going to run through fairly quickly. We want to figure out the following 6 things. We need to know what the minimum or fill pressure is, what the maximum pressure is, what the minimum temperature of the system is, what the maximum temperature, the fluid type, and the system volume. And I think that, have we gone through the HS2 diagram on Taco Tuesday, Brett?
Yes, we have, although we have
So
others.
today I'm going to arbitrarily pick a volume for my system, but if you're using the HS2 software, that software calculates the system volume very accurately for you. So the methodology is just a matter of accuracy, but the concept's exactly the same. So how do I figure out what the minimum or fill pressure is? Well, let's take a look at a very simple problem here. Given a 75-foot tall office building, let's find the expansion tank size. And here it is. I've got a very, very simple 75-foot office building. And let's assume that my piping starts in the mechanical room, which is at the lowest level of the building, and it runs through the building, starts at the lowest level, runs vertically upward to the very, very top here. And I'm just kind of exaggerating for simple example here. I'm going to put a little Home Depot bucket there and a little valve. So my valve over here is initially open. So if I allow water to fill this piping system until I get a few drops of water out and I close my valve at the top, and let's say after the system is 100% filled and I close my valve at the bottom, what's the pressure? What's the pressure at the bottom of this in pounds per square inch gauge? Anybody know what that answer is? And while you're thinking about that, what's the pressure at the top of my little example here?
I'm watching, baby. I'm watching.
Did anybody give us a pressure at the bottom, Brett?
Well, 35. Well, 0, I think Gordon's saying at the top. 30, 32.4, same top and bottom. 32.4 PSIG, but add 5. 47.25 at the bottom. We're getting a bunch of answers here. I'm not sure you're getting what you want, though.
Well, that's true. At the bottom, if I just fill the piping system with water, and I don't turn anything on, I don't have anything expanding, I'm just measuring the pressure, I'd read approximately 32.5 at the bottom, and somebody had the correct answer, that would have 0 at the top. Well, we
Right.
don't want 0 at the top. We want something greater than 0. I'm just going to put 0 PSIG at the top here. We want something greater than that. Most people, when they design hydronic systems, will say that initially I want to have somewhere between 5 and 10 pounds. So we're going to rig the numbers. We're going to make 7.5 pounds. So if I add some additional water so that my pressure at the top of the building becomes 7.5 pounds, what's pressure going to be at the bottom of the building?
Someone typed in 40.
That's correct. So if I pressurize the system, so I have 7.5 at the top, I'll have 40 at the bottom. And if I have 40 at the bottom, I've just determined what my minimum pressure needs to be at my expansion tank if my expansion tank is at the bottom of the system in the mechanical room at the lowest point in the building, 40 PSIG. So I'm going to repeat this narratively, just go through here quickly and say that the minimum pressure is equal to the height of the building and converted into pounds per square inch gauge. So the height of our building was 75 feet. Divided that by 2.31, which came out to 32.5 pounds per square inch, which someone told us they did that correctly. And then if I wanted somewhere between 5 to 10 pounds, somewhere between 5 to 10 pounds at the top of the building. And the reason I want at least some pressure at the top of the building is for 2 major reasons. I want to have enough pressure to push the air out so it doesn't accumulate air. And secondly, I want to have enough pressure to make sure that if I have any equipment, could be a pump, could be a valve, that it's not cavitating. So I want to have positive pressure relative to the atmosphere at the top of the building so I can push the air out. In our case, we use 7.5 pounds. And if that was the case, and we would have 40 pounds. So we've determined the minimum pressure at the bottom of the building. Whoops, I've got this thing here I need to erase. There we go. So we've determined that the minimum pressure at the bottom of the building at the expansion tank is 40 pounds per square inch, which, by the way, is also known as the pre-charge pressure. And that's what we pre-charge the air side of this expansion tank. Now, this answers one of the questions that came up earlier. How much pressure do we want on the air side of the tank? Well, you have to go through this calculation, knowing the height of the building, what you want for pressure at the top. You do your calculation, and that becomes the minimum or fill pressure for your expansion tank, which is also the air side pressure, which in our case is 40 PSIG. Any questions about that, Brett?
Nope.
Okay. Now, what's important to recognize is that when we ship our expansion tanks from the factory, they are pre-charged to only 12 pounds per square inch gauge. And if you are going to connect one of our expansion tanks to this imaginary system, then you would have to pre-charge the air side to 40 pounds before you connected it to the system. It's extremely important to understand that you have to pre-charge the tank on the air side to 40 pounds before you connect it to the system. Once you pre-charge it to 40 pounds, because remember, it only comes from the factory, 12 pounds, then you can connect it to the system, and then you can set your fill valve to 40 pounds, and now the system minimum pressure has been established by the expansion tank. And that's one of the important characteristics of an expansion tank, is to be able to make sure that we're controlling the pressure in the system. Okay. So moving to the next thing, how do we determine the maximum pressure? Well, the maximum pressure generally is limited by the pressure rating of the equipment. So in our case, we have this air handling unit that's on the lowest level, and let's say it has a maximum design pressure of 150 pounds per square inch gauge. We have a safety relief valve over here, and we want to set the safety relief valve at roughly 10% below what the maximum pressure of the equipment, because you never want the equipment to see its maximum pressure. So if I set it at 10% below that, then that pressure for the safety relief valve would be set at 135 psig. 10% of 150 is 15. 150 minus 15 is 135. Now, a safety relief valve is a very simple device, and so we'd want to make sure that the pressure in the piping system was a little bit below the relief valve setting so that the relief valve doesn't drip or drip or leak. Sometimes they call it weeping. So we're going to set the pressure on the discharge side of the pump about 5 pounds below the relief valve setting. So we're going to set that 130 pounds. Now, let's assume for a moment that our pump adds 20 pounds to the system. And so if our pump adds 20 pounds, then the suction pressure wants to be a maximum of 130 minus 20, or 110. So if I have 110 maximum at the suction side of the pump, I'll have 130 at the discharge of the pump if the pump adds 20 psi, which is less than the relief valve setting, which is less than the equipment. So if I provide an expansion tank that limits the pressure to a maximum of 110 psig, the suction side of the pump, I now have the two pressures I need for selecting the tank. So we have the minimum pressure we said was 40 psig, the maximum was 110. The fill temperatures, typically the ground temperature, and in New England where I live, the ground temperature is fairly constant throughout the year at about 50 degrees Fahrenheit. And let's assume we have a heating system, and the design temperature, the heating system, becomes our maximum temperature. In my case, it's a heating system, and I've decided that the maximum temperature is 180 degrees. The next thing is to figure out what the fluid is. In my case, I'm going to assume that the fluid is straight, clear water. It doesn't have ethylene glycol in it, no propylene glycol, no chemicals right now. It's just clear water. And the final thing, as I said earlier, we need to know the volume of water inside the system. And for this example, I've estimated it to be 2,000 gallons. You'd have to use some type of software or manual process of adding up all the volume for the piping, the equipment, the valves, anything that's in the system, the terminal devices, in order to calculate the system volume. Or if you were using the HS2 software, it calculates that for you. So now we have all the information for selecting our expansion tank. So I'm going to go in real time to our expansion tank selection app. A little luck, go over here. And I'm going to go to Taco's website. And just to the right of center, it says selection tools. I'm going to click on that. And on the left-hand side, it says expansion tanks. I'm going to click on that. It's going to open up the expansion tank app. Now we're simply going to type in the values that we just figured out. Our system volume is 2,000 gallons. Our minimum fill temperature is 50 degrees Fahrenheit. Our maximum design temperature is 180 degrees Fahrenheit. Remember, we calculated our minimum fill pressure to be 40 psig and our maximum to be 110. I'm interested right now in a standard expansion tank. Click on search, and the software is going to do a couple of things. First of all, it's going to calculate what the system volume expansion is, and that's right down here. The system volume expansion. In other words, if I initially fill the system with 50 degree Fahrenheit water, and I heat that up to 180 degree Fahrenheit water, and I have an initial volume of 2,000 gallons, that water will expand an additional 53.44 gallons. I'm going to ignore the plain steel tank for a moment and just concentrate on the bladder style tank. So I'm looking for a bladder style tank whose steel container is at least 95.2 gallons. The first one the software has selected is 119 gallons. And the acceptance volume, which is the expansion volume, has to be at least 53 gallons approximately. This one is 119. By the way, since the tank steel volume and the acceptance volume are equal to each other, that's called a full acceptance tank. So this tank will do the job and meet all the criteria that we established over here. All of that criteria. If we did that with a partial acceptance, we still need to have a steel container that's at least 95.2 gallons. This one's 112 gallons. And its acceptance volume is 61 gallons, but since my fluid is only expanding approximately 53.4 gallons, then the steel container is greater than the acceptance volume, and so that's called a partial acceptance tank. So before I get into any of these other selections, do we have any questions, Brett?
Somebody's
Did I lose
questioning
Brett?
nope, somebody's questioning the copper and steel pipe. I'm sure you'll cover that. But anyways, go ahead.
Yeah, I will cover that in a few seconds. Any other questions out there? I know we went kind of quickly through the selection process, but most of the time when you can see the selection is very fast. Once you know what the 6 parameters are, once you establish those 6 parameters, using the app is the simple part.
Well, I consider 10% less for safety relief. I mean, that's
I mean, you know, different engineering offices have different criteria for setting this, or choosing rather, the safety relief valve setting. I set it at 10%. Other people might pick 20%, and I've actually seen designs where people pick 25% below the maximum pressure of the system components. So yeah, it's a little bit arbitrary. There's no specific code that says what you should select for your safety relief valve. But I generally pick a minimum of 10% below the maximum operating pressure I want in my system.
somebody's asking, what's the formula used for this calculation? So what's the formula behind the scenes?
It's actually a derivation of Boyles Law. If you're interested, contact your rep and we'll send along a calculation sheet so that you can see how Boyles Law is developed into a more extensive calculations so that you can figure out what the volume of the tank should be.
All right, so
But
this
it does
question,
start with that basic equation, P1V1 equals P2V2 at constant temperature.
this question I probably should have brought up earlier, Rich, then I apologize. Regarding one of the purposes of an expansion tank being system pressure control, does this mean that the expansion tank helps to keep a net positive suction head on the pump?
Yes, it does. In fact, in a closed loop pressurized system, assuming that you're within the parameters of the pressure rating of the components, you can increase the pressure at the suction side of the pump, or the minimum or fill pressure at the suction side of the pump, so that it's greater than the net positive suction head required by the pump. So yes, in a closed loop pressurized system, you can control the available pressure and make it greater than what's required by the pump.
And then I forget the answer to this question. What is the tank pressure limit? I think we can offer them up to 300, but our standard might be 150.
Yes, that's one of those things that I would look in our catalog data. If you need an answer, contact one of our reps and he'll be able to send over the literature and you can see exactly what the standard pressures are available. And I think you can also order a tank with custom pressures. And again, talk to your rep. They'll be able to help you with that information.
So someone's saying, what is the procedure for chilled water applications? It's the same, except maybe that temperature might be a little different. One of the temperatures.
Yeah, so in a chilled water system, I would still use a minimum or fill temperature of 50 degrees Fahrenheit if I was in New England. But for the maximum temperature, I typically use between 100 and 110 degrees. So someone would say, well, it's a chilled water system. Why would you ever have water temperature that high? Well, it's possible. In fact, it does happen quite often. Someone might build and fill a chilled water system before putting it into service in a building. And they might have everything finished, 100% buttoned up, ready to go, except they're not going to start the chiller. So it's going to just sit there initially with 50-degree water in it. It might sit there through a very, very hot period in the summertime, in which case the ambient temperature could increase, and the ambient temperature could get over 100 degrees. And if the chillers aren't running, the water temperature would cause the fluid to expand. So actually, I guess there was some records set in, was it Nevada that I was reading this summer? There was ambient
Quite a
temperature.
few.
Yeah, I mean, it really got up there. It was amazing, like over 120 degrees. So I typically, for chilled water system, pick the maximum temperature at about 110 degrees.
And we have two folks asking this question, and this is a great question. Can you oversize an expansion tank? What's the penalty? Or
Well,
can you? Is it
there's
bad?
no operating characteristic penalty. There's no penalty to the operating characteristics of a system if you should make the expansion tank larger than what you need. The only penalty is that you'll be buying more tank than what you need, so the cost is going to be more expensive, and the tank may be physically larger than what you can accommodate for space or real estate within the mechanical room. So the only two penalties are cost and space. There's no operating penalty if the tank is larger than what it needs to be.
Personally, if I was, I would err on the size of safety, if you know what I mean. I would.
Yeah, I mean,
I would
expansion
oversize
tanks
it.
are, they're a static device. They don't have any electric motors. They don't have any belts or fans or rotating parts. I mean, it's just so, to increase the size slightly to make sure that it's done properly is not a gigantic penalty. So in our example here, the first one was a CA 450. I don't honestly know what the next size, maybe the next size is a CA 500. Maybe you would know that, Brett. I don't know off the top of my head.
Yeah.
I mean, the difference in cost between one size and the next size up is negligible when you consider the overall scope of the mechanical system.
And then, oh shoot, I just, if a tank has full acceptance, why can't we use a 60-gallon tank in this example?
Well, you have to go back to Boyles Law, because ultimately, let me erase the thing here.
We're already after one.
So we'll just go quickly back to Boyles Law over here, which tells us that if you remember, this container we said was 200 gallons, and then we added 100 gallons of water, which compressed the air from 200 gallons down to 100 gallons. So there is a relationship between the size of the tank and what ultimately will be the maximum pressure in the system. So if you only had the tank sized for the expansion, there'd be no place for the pressure would go very, very high, because you'd be starting off with a large volume and a very, very tiny volume. And the smaller the final volume is, the much, much higher the pressure would be, which might be greater than what your system could possibly hold.
Awesome.
Well, we're just about at the end of our time period. Do we have one last question, Brett, and then we'll have to wrap it up?
I think you covered, I mean, so for a high efficiency boiler systems that use lower water temperatures, should you use 180 or 150?
You should use the design temperature of your boiler system. So if your boiler system has a temperature of 150 degrees, you should use that as your maximum temperature.
I mean, if there's a possibility it can go up higher, if something gets run away, then use the higher one. You know what I mean?
Well, yeah, I mean, it becomes a judgment call, because if you install if you specify and build a system that has a boiler operating temperature of 150 degrees, hopefully you've also put in the necessary safety devices, both electronically and mechanically, so that if the boiler should generate water temperature higher than it was originally intended, beyond its design, there's electronic devices that measure that temperature, which will shut the boiler off. If they fail, there are safety relief valves to relieve the pressure if the water temperature gets too high. So it's a judgment call, and there is no absolute answer to that question.
And I think this will be the last question. I apologize, we're over a little bit, but this is an important question. What does undersize an expansion tank cause to happen? Great question, John.
If you undersize an expansion tank, then you will exceed the maximum pressure that your system was initially designed to handle. So in our case, if instead of putting in a 100-gallon tank, if we put in, say, a 75-gallon tank, then it would exceed the 110 pounds per square inch gauge maximum operating pressure. And if that was high enough, it could potentially set off the relief valve. If there was a malfunctioning relief valve and there was no place for the water to go, it would damage equipment in the system. So undersizing has major consequences. Oversizing does not.
Thank you, Rich. Great job. Appreciate everyone's time.
At this point, thanks a lot, folks, for listening. I'll then turn it over to Brett to say the final goodbyes.
Rich, great job. But Boyles Law, baby, Boyles Law. P1 equals V1 equals P2 V2. Whew. I remember that from 1979. Anyways, thank you, everybody. Look for your email tomorrow, and we will see you down the road. Goodbye.